All right, this is, we should be looking at worksheet 4A, B. I'm not sure where this starts. This is a really important theorem that we're not really going to use. That sounds silly. Okay. It's called the intermediate value theorem. It basically says if you put values into a function and they're coming out positive, and then you put some other values into the function near those, and it comes out negative, it means somewhere in between there it crossed and had a zero. Does that make sense? If the function goes from positive to negative or negative to positive, it had a zero in between there. Okay. Now, that doesn't mean that there can't be zeros elsewhere, because a function could be positive and stay positive and have a bounce off the graph. Remember that? So there can be a zero. But back in the day, when we didn't have graphing calculators, Hofbauer's day, this was how we figured out where a zero was. We plugged in values till we found out that its sign changed, and then we could narrow down where the zero was for icky functions that we couldn't find zeros for, like x cubed minus 6x squared plus 2x minus 7. Okay, there isn't a cubic formula like there is a quadratic formula. There's no magic way to do that. Now that we have a graphing calculator, in my mind, this formula is kind of extinct, this theorem. Okay, so we're just going to kind of go, okay, I get it. And then we're going to turn around and use our calculator. So this is an example. They put in the integers from -4 to 4, and they got these values, okay? And they said, well, there must be a zero where? Well, I'm thinking there was a zero between -2 and -3, because it went from negative to positive. And there's another zero between 0 and 1, because it went from positive back to negative. And another zero between 1 and 2, because it went from negative, okay, which is clearly reflected in the graph that we all get to use a calculator for now. Okay, this is using the intermediate value theorem, and it's approximating zeros. The homework directions will say this. They'll say find what two consecutive integers the zeros fall between. Everybody knows what consecutive integers are. Okay, whole numbers next to each other, but they can be negatives. Okay, got it. I changed the directions. I think I wrote on your assignment sheet, find them to the nearest hundredth or something, or thousandth even. I don't remember. But you got a calculator. Let's just use it and move on. Does that sound okay? So here's another example. They're just showing you that even though they tested all the integers here, does it ever change sign, guys? Do you see all these are positive? And that's because the zeros are so close together in here that it's crossed. It's positive on both sides and stuff. So what they want you to do is not rely on this theorem, which is why we have a calculator. But again, you can't always rely on your initial window either, right? Do you know what I'm talking about? Sometimes if you zoom out too far, it'll look like it only crosses once, and if you zoom in closer, it could cross twice or something. So got to be careful. All right, this is the big concept, one of the big concepts for today, end behavior. Do you remember end behavior? Okay. The issue is it can be written several different ways. Our book uses limit notation, which we're not going to use. We're just going to use function notation. How do you say on the left? Does anybody know how you say on the left? Maybe I'm confusing you. Why is this not working? Okay. On the left would be as x approaches what? Negative infinity. Everybody okay? On the right would be as x approaches infinity. Yes? I don't know if you have this. I don't know if I put it anywhere. Okay. What is up? When the graph points up, we're saying what? The y value is approaching infinity. Okay? and down would be the y value approaches negative infinity. Now, I have to admit, I prefer to start with the x, to say on the left it's doing this, on the right it's doing this. Not the way they do it in calculus. I don't care which way you write it on your paper, and I might even say it that way, but I'm going to try to write it the way they do in calculus, which is they put f of x first. It totally doesn't matter, okay? We can write it first and say it the other way around, right? It just doesn't matter. What am I talking about? Well, let's get to an example here. But first of all, this is where you actually have it on your paper, I think. Eek. Really? Could you just work for me once without messing around here? Okay. This is supposed to be really together here. This is the limit notation, but do you notice down here it says x approaches negative infinity. So that's talking about the left, right? And then we say y approaches whatever. It could be positive or negative infinity if it's going up or down. Then this is the same thing. This is saying as x approaches infinity, which is talking about the right side. All right. We're going to use the ask feature of our table to check this numerically. We'll get back to that in a second. Oh my goodness, could you? All right, so let's describe the end behavior on this. Oh, look, I even put x first on the worksheet. That's how I like to do it, but I think we're switching back to the calculus way here. If I say the left side, what do I write in the first blank? X is approaching negative infinity. I don't know why it hates me. Okay, X, did I start the recording? Okay, all right. On the left side, what is this doing? Going down, so I have this. So in words, that means left, down. Is anybody confused about the words? Because I get really random things when people do this on the quiz. I'll get left, down, left, up. I mean, you have to be able to read it in words so that it makes sense, okay? This, if I want to say the right, I say x is approaching what on the far right? Infinity, and it's going up, so I'm going to put in infinity. So these would be right, up. We good? All right. Let's try it the way that they would do it in calc this time, okay? I know I'm not comfortable either, but let's, and we can do this, honestly. We can just switch the order. We can still say it the same way. What do you want to say? You want to start with the left side? So as x approaches negative infinity, what is the y doing? Why? Tell me why. The reason you're saying that. Because it's going down, yes. About to give up on this stupid thing. All right. The right side, we would say x approaches what? Infinity, because that's this direction. And what is it doing? It's going down, so we're going to say negative, y is approaching negative infinity on both ends, right? All right, are we good at end behavior? As soon as I use that stupid mouse, then this one doesn't work again. All right, use the graph of each function to describe the end behavior. This one is a not approaching infinity on the left and the right. Do you see that? As we go off to the left and off to the right, it's approaching a constant. So you can guess by looking at the graph, but we're going to put it into our calculator and use what's called the ask feature. So we're going to go and type in, oh, how do we type this in? 5x over x minus 2. Yeah, we have to have parentheses around both the top and the bottom. Well, Actually, I think we could buy without the top because it doesn't have plus or minus, but just do top and bottom anytime you have a rational function. What does that mean, a rational function? What's ratio? What's rational numbers? Written as a fraction. So rational function means something that's got a either x in the denominator or numerator and denominator. All right, if I do a zoom 6, standard window to see what's going on, it's not horrible, right? I can see a little piece of it. I should probably change. I don't really care because I'm going to use the table anyway. Where did I just lose the graph? Nope, that wasn't it. Sorry. Okay. Go to second window and turn your calculator to Ask Auto. Ask Auto, okay? It's going to say, what do you want to put in? Because otherwise you're going to be scrolling around in there forever trying to find end behavior. If we put it on Ask Auto and then we go to the table, does everybody have an X and a Y? You might have numbers in there, but does everybody have an X and a Y one at the top? Okay. They want to, what do you want to test for an X? Well, what's far off on the left? -10, okay? If I put in -10, enter, it says 4.16. It seems like it's close to 4 there, but it is greater than 4. So what could we try? Can we go a little further out? -20. Oh, 4.5. What's a really negative infinity kind of number? -100, -1,000, -10,000. My favorite, you realize that -10,000 and -9,999 are only one apart, but somehow it feels bigger to me when I put 9s in. So I usually do like -9,999. Okay. All right, that's just a moment of humor for you. Did you get 5? It's getting close to 5. Okay, really close to 5. Eventually, the calculator will round it to 5, but it doesn't ever actually hit 5. All right, what do you think on the right end? Kind of looks to me like it's probably doing the same thing, but can we just type in a big positive number? I'm going to do my 9 thing again. Now, I did get it to round to 5 by going out a whole bunch of places, but if I go on and put my cursor over that 5, it actually says it's 5.0001. Okay. All right, so what do we want to say about this function before we get too caught up in playing with the calculator? How do we say on the left end it's getting close to what? 5. So what are we going to write? Okay, we want to do that first. I'm going to put it back here. As x is approaching, not 5. On the left, the value of the function is approaching 5. And on the right, the value of the function was also approaching 5. Eventually, we'll learn the rules about rational functions. This one is what's called equal weight, so therefore it's leading coefficient over leading coefficient. Does anybody remember that garbage from last year? Probably not. Okay. Any questions on that one? Well, let me do. Well, let me turn the page. All right, I'm not even going to bother to write this one down. You good on this one? Left end would be number 5. Oh, the x would be -infinity, yes. But what's the left end? The y would be infinity. Right side, you would say x is positive infinity, y is positive infinity, because they're both up, okay? This is the section that says determine the zeros, and it says between which consecutive integers, but then find the actual 0 using the graphing calculator to the nearest thousandth, which is how many places? 3 decimals, okay? Do you need to do one of these? Is there one that maybe has a funky window? You want to try 9 or 10, guys? Which one? 9? Okay. I don't think we need to do both, but let's type 9 in. X to the third, arrow to the right, which I always screw up, plus 5x squared minus 4. Okay, I'm going to go back to standard window, see what I see. It wants all the zeros between -6 and +2. Did I type it in wrong? Did someone else find them all? Okay, I'm going to go trace -6 just so I see where my little cursor is. Oh, it's clear down at -40. So yeah, there's one somewhere in here between -5 and -4 maybe. Can you count your little tick marks? Does that seem right? Now, if you wanted to go back to the table, this would be a great time to actually have the table do auto, because then we could look and we should be able to tell that it changed signs in between. There we go. See, between -5 and -4, it changed sign. And between -1 and 0, it changed sign. And is that it? Oh, then back again between 0 and 1. It changed sign again. All right. So can you find those? Let's just practice. You guys find one or two of them. I feel like a few of you aren't as calculator happy as some of the rest of you. I'm just going to say this one over here, somewhere between -6 and -3. I'm not big on worrying about too specific. Anybody get -4.828? All right, the next one, again, this is why I don't like to cursor around, so I just type in values, but you can cursor around. The next one is between -2 and 0 somewhere. Oh, nice. What? Oh yeah, -1, 0. Like, calculator had to think really hard about that one. Oh, we don't put down 0. We're writing the zeros, okay. And the other one is somewhere between 0 and 2, somewhere around 1.828. Anybody get that one? Okay, I can't tell what I'm writing, so I'm just randomly. Okay, sorry, that's so messy. All right, so you get that idea. We don't need to practice that anymore. If I talk about this one, what does this say? If the voltage remains constant, which is the E, and the current, which is the I, were to keep increasing. Okay, so it says R equals E. If E stayed constant, and the resistance, which is down here, I'm sorry, the current were to get really big, so it approaches infinity. What happens when you have a constant number that's being divided by a number that's getting really, really big? Yes, R would become smaller. Or what is it talking about? The resistance would go down. So that's a great concept question that applies end behavior. Okay. What is this? Describe its end behavior numerically. So this is just another calculator typing question. Do we need to do one more where you put it in Ask Auto and check what's happening? I guess the big takeaway we can just guess and I can tell you what the answer is, what you would get on your calculator. What I need you to understand is end behavior does not always mean it approaches infinity or negative infinity. Got that? See this one on the far left and the far right, it's actually going to approach 7. If you put in this horrid function in your calculator, went to Ask Auto and put -9999 and +9999, be really close to 7. You take my word for it? How would you type this in? Parenthesis, 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 and then the divide 2 at the end, right? Or +2. I can read, just, Math symbols, they're tricky. Okay, can you pick out the multiple choice before we move on? Both ends are doing what? Up. That means f of x needs to be approaching what? Infinity on both ends. Yep. We good? You'd read through those and eventually, even though it's in limit notation, we can understand it. I'm just not going to make you write it that way, okay? As it still says under here, x approaches, we just leave off the word limit. All right, let's look at the other worksheet because we're going to analyze a graph for a whole bunch of funky behaviors today. All right. We are going to describe behavior of a function across an interval as increasing or decreasing. Does anybody know what that means? You should have done that one last year, I think. Anybody remember doing increasing and decreasing last year? I just want to cry right about now. Increasing and decreasing are describing whether the graph, as you read left to right, along a certain interval, is the graph going, the y values going up or are the y values going down? Does that sound familiar now? So if we have this graph, we would say from this portion over here, it is increasing. This portion in here, it is decreasing. And this portion over here is increasing again. Does that sound familiar now? And what are we going to call this point here? A local maximum. Does anybody know why it's not called an absolute maximum? Yeah, it goes higher over here eventually, right? It just means in this little area, it peaks and starts back down. And over here, this is called a local minimum or relative minimum, relative maximum. I guess the book uses those words. I'm confusing. All right, the maximums and minimums are called extrema. That's the fancy word they use to encompass all of those. It just means the extreme values, extreme max, extreme min. That makes sense? So if you see that word, what's extrema? Just means all the maxes and mins. All right. We're going to use x values when we state the increasing and decreasing. So on this graph over here, well, I can't move too fast for anybody today because I can't even move at all. All right, this piece of the graph is increasing, and so we say from negative infinity until -5, the graph is increasing. And then we say it is constant from -5 until 0. And then we say it's decreasing, from here on, so that would be from 0 to infinity. The graph is never at a single point, it's never increasing or decreasing. So when you talk about increasing and decreasing, you only use parentheses, which is kind of nice. You don't have to worry about, is it a bracket, okay? It also probably means I'm not going to be picky about it, but you should always just use parentheses. All right, so here's a graph that's constantly increasing. Here's a graph that's constantly decreasing. And here's one where it has a constant portion in the middle. Okay, it just says always use parentheses because it can't be increasing or decreasing at a particular point. All right, we're going to first do this question without graphing it on our calculator. We're just going to try to come up with these things, okay, by guessing and looking at the graph because it takes more time when we have to actually type it in. Let's see what we can try. So where is there a relative maximum? Here, here, are those both maximums? Okay, if we go from the left, the way they state this is a little bit tricky. It says the relative maximum value of the function, which is the y value, of 0 occurs at -1.5. Does that sound okay? So this ordered pair would be negative 1.50. It is a maximum Y value. Does that make sense? It's not a maximum X. It goes forever left and right, but it's a relative maximum Y value. And that's why we say the value occurs at. Now, on the quiz, I'm just going to let you write an ordered pair. You'd be happy with that? Just name the maximum as an ordered pair. Okay. The relative minimum, one of the, we're supposed to keep going left to right, I guess. Maybe that's why they have minimum next. What do you want to say here? What's the minimum value of the function down there? Oh, they did that funky thing again. That one's counting by twos, right? Oh, I hate this. So we call that negative 3.5 or something? Because this is negative 4 on the graph paper going up and down. This one goes by ones. This one goes by twos. Don't hate. Do you see how it goes 1, 2, 3, 4, and this one goes 4, 8? Ugh. I won't do that on the quiz. Okay. The X value where that happens, guys? At what X value? Negative 1/2? That sounds good to me. All right, where's this next red maximum here? What is the Y value you want to use there? Negative 2 point something? Sure, I don't care. I'm not going to be that picky. Because we're going to use our calculator to find these eventually, right? And what is the X value where that appears? 0.5-ish. All right, and then there's a minimum back over here. And the Y looks like negative 6, is that right? At an X of, that's by ones, right? So 1.5. Oh, that was just mean. Is there an absolute maximum or minimum? Absolute would be if both ends were going down, then the top would be an absolute because it never goes beyond there. Because this has one end up and one end down, there's not an absolute min or max because it's going to continue forever to go up and down. Does that help? If we have a parabola, it has an absolute max or min at the vertex. Does that make sense? Because the other ends are going the other direction. Okay. No. Okay. Describe the end behavior. The graph is increased. Oh, end behavior is up here. We gotta. Okay. I'm gonna put end behavior in here. The function is doing what on the what? What do you want me to say? Okay. If you go with left, we'd say negative infinity. And what do you want? Oh, that looks like a negative 8, huh, Bauer? Looks a lot like a negative 8 because it is. Okay. Negative infinity. How do we say it's going? Far left, it's doing what? Negative infinity. Okay. Then we need one that says on the right, doing what? Positive infinity. Everybody okay? I don't care if you write them backwards. If you write the X first and then the Y. Just as long as if it's a multiple choice question, you can pick out the one that means what you want it to mean. Okay? The graph is increasing. Oh, okay. This graph is so complicated. This is what I'm going to do. I'm going to use my magic highlighter. I love my magic highlighter. Just kidding. Oh, nothing works. Okay. Not going to use my magic highlighters because it's going to take too much time. We don't have any blue on this graph yet. I'm going to use blue if I can get it to work. Okay. What am I doing right here? Oh, really? What am I doing here? Screaming. Okay, what am I doing right there? No, left to right, it's going up. So it's increasing. Now, I state X values, okay? X values. What are the X values where it's increasing? Negative infinity to negative 1.5. Now, that X value should correspond to the X value at a max or a min, yes? Okay, where does it go up again? Can I use blue for this little piece right here again? That's from the first min to the second max, right? From negative 0.5 to positive 0.5. And then it goes up again over here, which started at this x value, which we called 1.5 to infinity. All right, so what's that leave for in decreasing? Yes, this piece in here, which I'm making really green, which is negative 1.5 to negative 0.5. It should be the holes in here, which this one in here was 0.5 to 1.5. Okay. The thing that is honestly the most helpful is when you sketch your graph, label on the graph those ordered pairs, because then when you go back to do this, you don't have to keep trying to figure out what was the x at this point, what was the y at this point, okay? All right, let's see if we can do, oh, we have a whole bunch. We haven't talked about concavity yet. All right, I'm just going to write this down. We're not going to get much practice on this yet today. Concave up is when it looks like this or it looks like this. It's happy, okay? I'm going to call this the happy face. That's concave up. Guess what down looks like? Okay, so this idea is concave down. The issue is it doesn't have to be doing both sides of the happy or the dip. Okay, when the graph does this, whoa, I don't think a graph can do that, Hofbauer. Okay, here, this is the idea, guys. There, somewhere between this maximum and this minimum, there is an inflection point where it changes from being sad down to happy up. Do you see that? This side of that inflection point, it's concave down. This side of the inflection point, it's concave up. The inflection point, we are only going to learn to estimate. We cannot calculate the exact inflection point until you get into calculus and use a derivative. So we just have to guess, which makes it really easy because I'm going to let you guess, okay? But you will have to identify that to the left of this, it's concave what? Down, and to the right, it's concave up. All right. Now, that takes us to practice. I'm going to skip all this other stuff, and I'm going to try... All right, let's try number 1. See how far we can get. We still have almost 5 minutes. Yes, absolutely. 2x to the 6th. Guys, I need everybody type in or this isn't going to... So I need to know who's got calculator issues. 2x to the 4th minus 9x squared. Double check that you have it typed in correctly. I'm going to start with a standard window and I get... Yeah, it's not great. What could I do to make this look a little better and easier to see? Actually, I don't think I want to increase anything. I just want to look at this little area in here. You could probably do a zoom in. I'm just going to change my x to like -5 to 5. All right. Now I'm going to go over here and I'm going to sketch it and write down what I used for a window. And go up here and hope it works. we have 1, 0, 0, and that is and somebody tested it, it's actually 0, 0. Awesome. Okay. What else? Is that negative? No. And minus 5 point. Okay, sorry, I've gotten that fast. Is this one symmetric or not, guys? Let's see how much of it can. Oh, I need you to estimate. I need you to. No, I'm not using it, but I'm going to. Okay, let's talk about increasing. What is it doing over here? Increasing. So from negative, you can tell what x value. 0.97. Increasing. Where's another spot that it's what's over here with all right. Axis. Go back. Only one is what all right. But you also those 4. 5. Right. So we're kind of in the middle of this, but tomorrow is all about finishing this idea up, okay? I'm not doing anything new tomorrow. We're just going to finish concavity and all that good stuff. Yes, I am.